Our next tutorial problem involves the conveyor bracket hole diameters A, B, and C. We're asked to determine the range of values containing 70% of the population of each measurement. To do that, we'll compute the population mean and standard deviation, and then we'll find a z-score and look that up on the one-sided normal error function. So the bracket measurements that we're using, we can take a look at here. Just as a reminder, we're looking at A, B, and C hole diameters. So we'll switch over to take a look at the data, and we'll start to get that. We're going to need to get means and standard deviations of our conveyor bracket measurements. And so we can grab all of the data and then insert a pivot table like we've done before. And that's a quick way of getting the mean and standard deviation. So the rows will be measurement component, and we don't need the totals here. And then the values will be the measurement value mean or average, and then also the measurement value standard deviation of the population. We'll filter on section number. So we'll only bring in one section of data, which we'll consider the population. And then we'll filter on the measurement components that we need. And in this case, we'll just keep conveyor brackets A, B, and C. Okay, and so here we have our data. We can see conveyor bracket A, B, and C. The average value for hole diameter A is 34.41, and a single standard deviation is 4.08. For B, it's 45.31 millimeters, standard deviation of 3.82. And for conveyor bracket C, the average is 28.18, and the standard deviation is 1.35, which is a little smaller than for measurement A. So we are asked to compute the 70% range. And so with that, we'll define the probability range that we're looking at. Probability range. So what we'll just call probability of 70%. And we're being asked to find the range within 70%. Okay, we're going to assume a normal distribution. And we're going to assume that we have the population represented. Okay, we'll take a look at a statistics textbook where we can look at a normal error function to solve this problem. So this is the Figlioli and Beasley text. This is the one-sided normal error function, which shows a shaded region here as a probability of a value between 0, the mean, the normalized mean, and Z1. So that's all tabulated as is typical in a textbook in a table like this, table 4.3. In this case, it's a one-sided integral. This all has to do with describing the behavior of a population, assuming the Gaussian distribution here, and then redefining the variables in terms of Z, which is X, a value of a measurement, minus the mean divided by the standard deviation. Because that's symmetric, it's common to tabulate that one-sided, or where it's essentially the probability has to be multiplied by 2. And so to get our probability, we need to go back here and say, okay, well, P that we're interested in is actually 0.70 divided by 2, which is 0.35 or 35%. So we need to find that in our Z table. If we scan the probabilities here, we see the closest Z value is right here, 35.08. It's not exactly 0.35. So we'll just use that. The Z1 value is 1.0 plus 1.04. And so our Z, we'll just put this here, our Z is 1.04. Okay. Well, how do we use that? We're just going back to the definition of Z, this standard normal variate right here. We're just going to add or subtract that with the mean. And so to get our low range. So we'll just call this X low for 70%. What we'll do is we'll take the mean value and we'll add 1.04. We'll just put it in here, 1.04, this which is the Z value times the standard deviation. And that gives us 0.3865. Our high value for our 70% range is the mean value plus 1.04 times standard deviation. And so actually this should have been minus for the low value. Fix that real quick. So 38.18 is the low and 38.65, 30.18 and 38.65. And then we can just fill that down. And these are then the range limits for 70% of the data for brackets A, B, and C. Okay. And these are also in millimeters as well. So that's the short answer to this problem. If we wanted to make our own Z table, for example, one of the things we could do is we can use this norms S distribution to tabulate our own Z value, or we can just use a normal inverse function or normal S inverse function to get the similar value for the Z. Now, when we do that, we have to be careful of whether or not we have a one-sided solution shown here or a typical Z table that has Z represented from all the way on the left all the way up to here. And so sometimes we have to subtract off 0.5 to get that interval. We can go back and we can take a look at what this looks like for this guy right here. So let's assume an X value in millimeters for measurement A. We'll start at 20 millimeters, and then we'll just add 1 to that, and we'll go down to, that's about 50. Okay, and from there, then we'll compute the probability of that X occurring using a normal distribution. Okay, so we can do equal norm distribution, and then make sure I have that function right, norm dist, and then from here we put in the value that we're interested in. Maybe make sure I have the function right, norm dist, and then yeah, this value is the value we're interested in, and then the mean and standard deviation. And then we're not interested in the cumulative, so we'll compute that right there. That's the probability associated with an X value of 20 for bracket A. We can put that in percent there, and then we can scroll this down. Before we do that, we'll go ahead and lock in these values here with dollar signs and fill that down. So with this, we can actually get a look at what the distribution looks like. So we can chart that. It'll default to a histogram, which is not quite what we want. We can put a nice line, continuous line here, and we can see that we have a bell curve. And for measurement A, which has an average of 34.41, it looks like right here. Okay. We can make that more of a shaded region, and then we can add the probability of 70% of X here. And so looking at our range here, we're about 30 to 38. And so we'll just approximate that by giving these values numbers, and then we will go back to this chart. We'll edit the chart, and then we'll add a series. And we'll pick that, and we can see the 70% range for bracket OAB or OA. And so that's essentially answering the question of the range limits for these bracket measurements. Notice that this one is a little tighter. Hopefully that's more accurate measurements reflected in that. And some of these are have rather large ranges for that. So that is the core response to the question about conveyor bracket measurements represented here in problem 4.2.3.